Welcome back to Chips and Salsa, where we talk about security and intel. I'm Jerry.
I'm Krobe, and today our guest is Yossi Oren, who's a senior lecturer at Ben Gurion University in Israel, and he's also part of Intel's Researcher in Residence program.
Yeah, a lot of people may not be aware of the breadth and depth of Intel's involvement with the academic community, especially in the security space. The Security Researcher in Residence program is just one of our many engagements.
Right. The RIR program is where folks like Yossi can spend a year working with Intel, and one of the things he worked on was the Hammer Scope, which we did a video on with episode 32 with he and the other researchers for that.
Yeah, so let's cut over and hear from Yossi about his experience over the last year. Yossi, thank you for joining us again for this episode of Chips and Salsa. I know we asked you this the last episode, but can you tell us about yourself, what you do here at Intel and in your university?
So, hi, Jerry. Hi, Krobe. So usually I'm an assistant professor at Ben Gurion University. It's a university in Israel. And my lab is called the Implementation Security Lab. We study how things can be attacked by looking at the way they're built, not the way they're designed. So looking at physics and sensors and stuff like that. And one thing that we really like to study in my lab is side channel attacks. I might explain a little bit what it is. And right now I'm in Intel's Security Assurance Division in a lab called iSTARE lab, the lab where Intel tries to hack its own chips.
So could you maybe explain a little bit more about the Researcher in Residence program that you're working with us here on?
Well, Researcher in Residence is kind of a new idea. It's a way for academics and Intel to engage together in a meaningful way. So right now I'm assigned to a lab at Intel, and I work with the excellent researchers there. And there are a few really good things that can be done using this program. First of all, I can serve as a way of bringing out the goodness and the richness of Intel's own internal researchers by writing academic papers with them. And it also works the other way. So I can look at Intel and be really inspired by the unique challenges that Intel has. And then think about what can I do as an academic, as a researcher, to explore these ideas. And so this really is something that you can't see when you're not inside an organization. See the unique challenges and trials that a security aware organization has. And there's all of cool things I can do because I have, let's say, backstage access, or what's called white box access to everything that Intel does, everything I ask to see. And I probably imagine after this year is gone, they're going to zap my brain, so I forget everything. And it's a good thing we have this video, so I'll have some kind of memento of my moments at Intel.
I guarantee you, Krobe has the glasses to the zap.
These are anti-mind zapping glasses. Okay, well done. Okay. And I have to say, it's something that's really remarkable to me. Learning at the culture of an organization, how to do security research, how to do security awareness, how to do security response in an organization with 100,000 people or more. And that culture and how it works even outside research, especially in times of trial. It's fascinating to me.
Yeah, incident response is, I don't know. To me, it's the best place to work at Intel. Because we get to sit here and talk with guys like you. So, Yossi, what do you see as some of the unique challenges at Intel, and how do you take that back to the university?
So I think one of the things that you hear a lot around Intel when you talk to people who are thinking about how to do security is a concept called shift left. And shift left, I think, it's worth explaining. So I prepared a teaching aid, but unfortunately, my cat ran away when I was doing the rehearsal. So I have this artificial teaching aid which I prepared. So let's imagine This is a process of developing a product. So it starts, of course. I hope this is on the left. If not, tell me and I'll flip it around. Is this the left? Because I'm we write right to left. I think it's going to be this way. Okay, let's do it this way. You'll flip it in post. So so first of all, when you design a product, you have to do this head stuff, this thinking, right? You have to think. You have to design the product, and you write design, and you do high level design, or architectural design, specification. Then you go down to nothing's written down, nothing that can execute is actually written down, and then you do the hands. This is the next step where you actually start writing this whatever you're building, probably a chip, and you're writing stuff, and not everything works. You have all these components, and you're writing them, and then you have this prototype ready. Now you're like it's starting to learn how to walk, and you're doing this verification inside your company. You're getting ready to release it, and then of course this is rated PG, so this is there's a part here which actually releases the product, and then there's the tail. During the tail, the product is in the hands of customers, and you have to support them, and you have to release upgrades to them, and do an incident response to them. And then at the end, they're probably going to go and get another product. So at any stage of this process, you can have discovery. You can discover bugs and also security bugs in your project. And shift left means basically that the more you go to the left in this life cycle of a product, the happier you are, the less cost to fix this project, this bug, this vulnerability, and the less impact on customers. So usually, if I'm a security researcher in academia, I come around just around here. Okay, so the product has been released, and I go quickly and buy, let's say, 4 pieces of this new piece of hardware and start hacking at it and reading the documentation. And then if I find something here, then obviously a lot of people are going to be in trouble. There's a huge scramble to fix it. So shift left means let's try to fix these or find these bugs as early as possible. And now it's, during testing, internal testing, that's a fantastic place to do. And one of the things Intel has what's called a yearly security report. And you can see that Intel is very good at finding these bugs during what's called verification. So that's fantastic, and it saves a lot of trouble to external teams. But you can actually start and think about how do we do it even earlier? How do we do it when we just have these, okay, I just wrote this driver for some piece of hardware. This hardware doesn't even exist, okay? But I've got these bunch of lines of code. I need to find out if they have security vulnerabilities. It's not easy, but it's very, very important to Intel to do it. And there's a huge effort in getting this right, including reinventing ways of rethinking about how does the compiler need to look like, how does a simulation environment look like. It's fascinating to me to look at. And even if you do it in the design, this is like getting the mindset, getting people to think about security. So it's really insightful to me to see how this thinking goes, and it's also interesting to see how you respond to a bug which you find earlier in the project.
It's very interesting. Can you share any insights of what you've learned, like how we can raise awareness to the engineers that are part of this process?
Well, let's be kind of compassionate right now. Line engineers who are sitting and writing, they want to get their projects done. They want to be a source of pride and profit to their organization. Giving them security awareness is wonderful. I think it's something which it's great. It's essential. But the right thing is probably going to be to give them the right tools.
Okay.
When I'm designing a function, I'm writing, let's say, when you do a hardware design, there's something called a state machine, which is basically, if you imagine the elevator, you press button number 2 when you're on floor number 2, what should happen? Number 3 and number 4, all these buttons, all these reactions. So you have to design a state machine. And when an engineer writes this kind of state machine, and one of the states is not defined. So the engineer doesn't declare what the machine should do at that state, maybe because there's nothing meaningful that the system should do in this state, then the compiler just goes ahead and does whatever is easiest on the hardware, or on the speed, or on the battery life, or whatever. And sometimes these shortcuts can cause all sorts of security catastrophes. So one thing you can do, for example, is write a compiler that says, hey, listen, I'm going to make this assumption that this state you didn't write down, I'm going to do something. Why don't you look at it again and see if that's the right thing you want to do? And this is one thing that you can do earlier in the life cycle. When you pull in components for other people and mix them together, do you realize what's going on with these components? Are they the supply chain, what's called? Are they good? Are they being patched? Are they being maintained? Are you keeping track with all the stuff that's going on outside your project? These are things which are on the desks of the engineers and help them work better, even if they're not really the security advocates of the organization.
What is next for you? How do you plan to carry the things you learned back to academia with you when you head back?
So actually, that's a really great question, because obviously there are things that I've learned here that are not going to be coming out with me. But yeah, but there are things, I think, a focus on defense, and a focus on defense that makes sense, right? Things, computers are there to do stuff, and they need to get things done. And when you write a defense, it needs to, also work that way. It needs to keep getting things done. I think one of the things which is really exciting and at least as a researcher are very interesting to me, and something which the iSTARE lab, which I'm located at in Israel, is the right place to research, is the fact that what's called the threat model is changing. And this is so a threat model basically means what am I assuming that the attacker can do? So it used to be that the attacker could, get infected with, infect the computer with a virus or stuff like that, or maybe, connect to the network, to the device and do stuff. But now things are happening. One thing that's happening in the threat model is that computers, or at least computers with secrets in them, are becoming vulnerable to what's called physical attacks. Physical attacks means that the adversary, the bad guy, has the device with the secrets, holding it, and this bad guy can do whatever to this device. It could be lasers, it could be drilling into it with a microscopic drill, it could be making any assumption the device has about the environment. Challenge is the temperature, radiation, vibration, whatever you want. And what's kind of mind-boggling is that when Intel designs a product, when we're up here, right, these products are going to be out there in 5 years, and they're going to be used for 5 or 10 more years. So I need to think the attacker of 15 years from now, what's the budget of this attacker? What are the capability of this attacker? And what access do they have? How much time do they have? And this is such a challenging proposition, I think, that's going to be really affecting the kind of defenses you can build.
It's some really interesting insights. And hopefully, as you go back to academia, you'll consider continuing to partner with us. We've had a lot of really great collaboration with the security research community. It's exciting that hopefully now that you're a little more educated into some of the inner workings of stuff, that we can have some productive collaboration in the future continuing.
Yeah, I'm looking forward to it.
Well, Yossi, it was great to talk with you again.
Thank you.
Good luck in the future, and like Krob said, looking forward to more collaboration in the future. And thanks for joining us today.
Thanks a lot, Krob. Thanks a lot, Jerry.
Wow, what a really interesting conversation. That Yossi is a very smart fella and has some amazing teaching aids.
Yeah. I think it's great to have folks like him working with us over a year period of time, and taking the understanding and challenges back to academia and help having that help inform the things that they're teaching their students. So it's pretty cool.
Yeah, very much a two-way street where both, companies like Intel benefit from the access to his brain power and insights, and then he gets to take that back to his practice at school. So it was a very exciting episode today.
With that, that's a wrap for this episode of Chips and Salsa. Thanks for joining us.
Bye.